So, good morning, students. Yesterday, we have discussed some basic definitions on complex number, then the conjugate of complex numbers. Also, we have discussed some examples on it. Yes. So, today we will discuss here a de Moivre's theorem. So, the statement of this de Moivre's theorem is if n is any positive integer, then prove that r raised to n in bracket cos n theta plus sin n theta is equals to r cos theta plus I sin theta raised to n. So this identity we have to show. So let us see here the proof of this theorem. We prove this by mathematical induction. If n is equals to 1, then r in bracket cos theta plus I sin theta is equals to r in bracket cos theta plus I sin theta. Yes. So this identity is true for n is equals to 1. Now, by mathematical induction, we have to show here this result is true for any n is equals to k. So let us see here. That means r raised to k cos k theta plus I sin k theta is equals to r in bracket cos theta plus I sin theta raised to k. Yes. Now next one, we can write this left hand side r in bracket cos theta plus I sin theta raised to k plus 1 is equals to r in bracket cos theta plus I sin theta raised to k, and in another bracket you can write r in bracket cos theta plus I sin theta. So just you can take this r raised to k and this r is outside, we get r raised to k plus 1, and write in the bracket cos theta plus I sin theta raised to k, and in another bracket cos theta plus I sin theta. Now you can multiply these two brackets, we get r raised to k plus 1 in bracket, you can multiply this cos theta to each and every term of this first bracket, we get cos k theta plus I sin k theta, cos theta plus I sin theta. So this is equals to r raised to k plus 1, multiply this one, we get cos k theta plus I cos k theta sin theta plus I sin k theta cos theta plus I square sin k theta sin theta. So which is equals to r raised to k plus 1, you can collect the terms of minus and collect the terms of real part and collect the terms of imaginary parts. So here it is cos theta minus sin k theta sin theta plus I in bracket cos k theta sin theta plus sin k theta cos theta. So which is equals to r raised to k plus 1, and in bracket if we know cos A cos B minus sin A sin B is cos of A plus B. Yes. So by using that identity, you can write cos of k plus 1 into theta plus same thing here cos A sin B plus sin A cos B, you can write it is sin of A plus B, and that's why we can write here plus I sin of k plus 1 theta. So this is the result is true for any n is equals to k, and that's why by using mathematical induction we will show here the result r cos theta plus I sin theta raised to n is r raised to n cos theta plus I sin theta. So this is the de Moivre's theorem. I think all of you are understand very well the proof of this theorem. Yes. Now next we will see here the example on de Moivre's theorem. So by using de Moivre's theorem, we have to find here the two complex numbers satisfying z square is equals to 2. Here z is a complex number. We have to satisfy this one by using de Moivre's theorem. So let us see here the solution of this expression. You can write here z square is equals to 2 as 2 in bracket cos theta plus I sin theta. So how we can write this one? It is by using the statement of de Moivre's theorem. So which is equals to 2 cos 2 pi k plus I sin 2 pi k. After that, you can take the square root of this z square. Z is equals to root 2, and so this root 2 is equals to, you can write cos theta plus I sin theta raised to 1 by 2. Yes, you can take the square root, and this is equals to 2 cos, you can take this 2 and this 2 is here, and that's why here 2 cos pi k plus I sin pi k. So now you can run this expression for k is equals to 0. Then if you put k is equals to 0 here, we get the value of z is root 2 cos 0 plus I sin 0. So you know the value of cos 0 is 1 and the value of sin 0 is 0, and that's why the value of this z is root 2. If we put k is 1 in this expression, we get the value of z is root 2 in bracket cos pi plus I sin pi, because here the value of k is 1. So the value of this expression, you know, cos of this pi, what is this cos of pi? It is minus 1. And what is the value of sin of pi? It is 0. And that's why the value of z is equals to, it is a minus root 2. Yes, just you can put the value of sin pi and cos pi here in this expression. We get the value of z is minus root 2. So is this clear? Now this is the next example we have to solve again by using De Moivre's theorem. So three complex numbers satisfying this expression z cube is equals to 1. So how? So just you can write z cube is equals to 1. Then you can apply or use the De Moivre's theorem. So you can write cos theta plus sin I sin theta, which is equals to cos 2 pi k plus I sin 2 pi k. Yes. So which implies the value of z is cos theta plus I sin theta raised to 1 by 3. Just you can take the cube root. Yes. So once you can take the cube root here, again you can take here also the cube root. So that's why it is cos of 2 pi k by 3 plus I sin of 2 pi k by 3. Yes. Now you can put the value of k is here first 0. So what we get? If you put the value of k is 0, we get cos 0 plus I sin 0, and you know the value of cos 0 is 1 and the value of sin 0 is 0, and that's why the value of this z is equals to 1. So are you getting my point here? Yes? Okay. Now if you put k is equals to 1 in same expression, we get the value of z is cos of 2 pi by 3 plus I sin of 2 pi by 3. Yes? Just you can put the value of k is here 1. Now you know cos of 2 pi by 3 is minus 1 by 2 and the sin of 2 pi by 3 is root 3 by 2, and that's why here the value of z is minus 1 by 2 plus I root 3 by 2. Similarly, if you put the value of k is 2, then the value of z is cos of 4 pi by 3 plus I sin of 4 pi by 3. Yes, just you can put the value of k is equals to 2 here in this expression. We get this one. And you know cos of 4 pi by 3 is minus 1 by 2 and the sin of 4 pi by 3 is minus root 3 by 2. So just put these values, we get the expression z is equals to minus 1 by 2 minus I root 3 by 2. So in this way you can use De Moivre's theorem in the same these previous two examples. Now look at here, next one. Now see here the definition of a function. So what do you mean by a function? So function is, if you take the two sets D and R, so you can apply that f from D to R. So whatever the value of any number or any variable in first set D, the associated value is in second set R. So that association is called as a function. So look at here. The function on a D to R means f is a function from D to R is a law. F which associate the each point P in D. Already I have told you. So the point P is in that set D. Exactly one point in R means whatever the value of that P, the associated value in R is, there is only one point. So which is denoted by f of P. So the set D is called as domain of that function f, and the set R is called as the range of a function f. So look at here in the figure, we will see here is the P is the point in a domain D. If we associate a function from D to R, then the value of this P in R is f of P. Yes. Similarly, if you take the point Q in a domain D, then the value of this Q if function f is associated from D to R, so the value of this q here in this function R, in this set R is f of q. So this is called as a function. So is this clear? Yes. Now we will see here the some properties of this function. We say that the two functions f and g are equal. When we say that these functions are equal, when f and g both are equal and they have the same domain D, and the value of f of p is equals to the value of g of p for all the points p in a domain D. Now see here the next definition. It is a complex valued function. If f is a function from D to R and if the values of f is the set of complex numbers. So the difference between is previous definition is a function and this is the complex valued function. It means the set D is here complex number. This is the set of a complex number, and that's why that function is associated with that domain is called as a complex valued function. Yes. So the function f is called as complex valued function. So if f and g, now we see here the some properties. If f and g are the complex valued function with same domain D, then these three are whole. The first is f plus g of p is equals to f of p plus g of p. Second is fg of p is equals to f of p into g of p. And the third one is alpha is any number is multiplied here alpha f into p is alpha in bracket f of p are also a function with a domain D. So again there is a remark, every complex valued function f defined on a domain D gives rise to two real valued function, this real of f and imaginary function f. So they are defined as real function f at p is real function f of p. Imaginary function of f of p is imaginary function of f of p. So for all a point p in D. If real function f and imaginary function f are called the real and imaginary parts of that function f which is represented, and we can write that is f is equals to real part of function f plus imaginary part of function f. Now look at here some remarks, but before that we can see here the definition of a limit. So already you have studied such a definition in 12th standard. So suppose that f is a complex valued function defined on a real interval I, then f is said to have a complex number L as a limit at a point x0 in interval I, and we denote it as a limit extends to that point x0, f of x is equals to L, or f of x tends to L as x tends to x0. So when this limit is exist, if f of this mod of f of x minus L is tends to 0, as 0 is less than mod of x minus x0 is less than infinity. Sorry, x0 is tending to 0. So it means that there is a number epsilon greater than 0, there exists a number delta greater than 0 such that this identity f of x minus L is less than epsilon whenever 0 is less than mod of x minus x0 is less than delta. Yes, so this is the definition of a limit. Next one, now we will see here the remarks on that definitions. So an interval I is the set of real valued x satisfying one of the 9 inequalities. So I have shown here these are the 9 inequalities. X is in between a to b. So this is the closed interval. So this is the closed and open interval. This is open and closed interval. Here open interval. This is a closed interval and infinite is there. So this x is in between a is less than or equals to x is strictly less than infinity. Here a is strictly less than x is strictly less than infinity. So x is in between minus infinity to infinity. Here x is in between minus infinity to b, and here minus last one minus infinity is less than x is less than or equals to b. So where a and b are distinct real numbers. Second remark, if f of x is tends to L and g of x is tends to m, then f plus g of x is also tends to capital L plus m, and if the product of two functions fg of x is tends to Lm, suppose that the third remark, f has a limit L is equals to L1 plus I L2 at a point x0 where L1 and L2 are real, then since you know these expressions are satisfied, just you can see here, and thus we can say that a real function f at x tending to L1, imaginary function x as tends to L2. Conversely, if real function f and imaginary function f have limits L1 and L2 respectively at x0, then the function f will have the limit L is equals to L1 plus I L2 at a point x0. Now let us see here, again the next definition is a continuity. So a complex valued function f defined on an interval I is a continuous at x0 in I if f has the limit this one. Equivalently, we can say that a function f is a continuous at a point x0 if both real part and imaginary part of that function are continuous at a point x0. So we say that f is a continuous on an interval I if it is a continuous at a point of the interval I. So the sum and product of two functions which are continuous at x0 are continuous. Yes. So this is again the definition of continuity. Now let us see the definition of a differentiability. So the complex valued function f defined on an interval I is said to be a differentiable at a point x0 in that interval I if this ratio means f of x minus f of x0 divided by x minus x0, where x is different from x0, has some limit at a point x0. So this is the definition of a differentiability. Now look at here, again you can say that f is a differentiable at a point x0. So we can define the derivative at x0 is f dash of x0. You can denote it as f dash of x0, and you can see the limit. If f dash of x exists, then the limit is f of x minus f of x0, x minus x0 minus f dash of x0 tending to 0. Yes. So if f is differentiable at a point x0 if both real part and imaginary part of that function are differentiable at a point x0. So the derivative of f at x0 is given by this one, f dash of x0 is equals to real part of f dash of x0 plus imaginary part of f dash of x0. So this is the definition of differentiability. So now this one is the remark on that differentiability. If f and g are differentiable at x0 in an interval I, then the addition of these two functions means f plus g, and the product of these two functions means f into g are also differentiable at that point x0 in an interval I. So look at here, these are the two basic properties of differentiability. F plus g dash of x0, we can write it is equals to f dash of x0 plus g dash of x0. Second one is fg into dash, means it is the product, and then you can take the differentiability at x0 is equals to f dash of x0 into g of x0 plus f of x0 into g dash of x0, means this one is the product rule. First function, derivative of first function, you can take the second function as it is, plus you can take the first function as it is, and then the derivative of second function. Now look at here the definition of integrability. So complex valued function f with the domain x is in between that closed interval is said to be integrable if both real part and imaginary part are integrable. Yes. So look at here the definition of these integrals. Integration over a to b f of x dx, which is equals to integral over a to b real part of that function dx plus I into integration of a to b imaginary part of that function f of x dx. So this is the definition of integrability. And now look at here the remark on that definition of integrability. Every function f which is a continuous in a closed interval ab is integrable on that closed interval. And the second remark is, if f and g are integrable in a closed interval ab and alpha and beta are two complex numbers, then this equation is whole. So what is this equation? A to b alpha f of x plus beta g of x dx, which is equals to alpha into a to b f of x dx plus beta into a to b f of x dx. So today in this lecture we have discussed De Moivre's theorem, then we have discussed some examples on De Moivre's theorem, then we will discuss some definitions, the definition of a function, then definition of a complex valued function, then definition of a limit, continuity, differentiability and integrability. Yes, so I hope you have learned or you have understand this very well. Yes, so today we will stop here. Thank you.